So now we're going to look at binary search tree Big O. In order to do this, we'll have to do some simple math. So the number of nodes in this tree right now, obviously, is 1, but you could also write this as 2 to the 1 minus 1. 2 to the 1 is 2, minus 1 equals 1. And you'll see why I'm doing this here in a second. But if we have a second level like this, this is 2 to the 2 minus 1. 2 to the 2 is 4, minus 1 is 3. 2 to the 3 minus 1, 2 to the 4 minus 1. Now, as we get into very large numbers here, that 1 is insignificant. So let's remove this, and we'll say this is approximately 2 to the 4 nodes. This is approximately 2 to the 3, and 2 to the 2, and 2 to the 1. Now, if you're going to look for a node in this tree, it's going to take 1 step, obviously. But when we go to 2 levels, let's say we're going to look for the number 76, that is 2 steps. So we have 2 to the 2 nodes, approximately, and it took us 2 steps to find something. Let's say we're going to look for the number 27. It is 2, 3 steps. And if we were going to look for the number 49 in this case, it would be 2, 3, 4 steps. We have 2 to the 4 nodes, and it took 4 steps. So it's 4 steps to find something. It's 4 steps to remove something because you have to iterate through the list, find the node, and then remove it. And it's also 4 steps if we're going to add a node. If we're going to add a node under that 49, we would have to iterate through 4 steps, and then we could insert it. So that means that all of these are O of log n. And O of log n is very efficient. So remember, O of log n is achieved by doing divide and conquer. So let's bring our tree back here and show how it is that we're doing that. So if we're going to look for that 49 node again, we start at the top and then we go right. And when we do, we just made it where we never have to look at anything that's on the left of the 47. So we are effectively removing these from the search. And that's not a big deal when you have a small tree like this, but if you had 1,000,000 items in the tree, you just made it where there are 500,000 items that you don't have to look at. And then from here, we're going to go left. And now we have made it where half of the remaining nodes don't need to be looked at, like that. And then we finally come down to the 49 node, and we have done that again. And that is divide and conquer. So let's bring all of this back. So for our examples for calculating time complexity so far, we have used a perfect tree. And a perfect tree is going to give you your best possible scenario. And remember, we measured best possible scenario with omega. You're more likely to see a tree that looks like this. But even in this situation, you would say that this is roughly log n. But now let's look at our worst case. Our worst case would be if we had a node, and then the next one was greater than, and it goes to the right, and the next one is greater than that, and it goes to the right of that one, and the next one is greater than that, and it just keeps going on and on in a straight line. If the tree never forks, it is essentially a linked list. So let's say we want to go look for the 91 node. How many steps would it take? It would be 1, 2, 3, 4, and we have 4 nodes in the tree. That is O of n. So the big O of a binary search tree technically is O of n, not O of log n. So let's bring our other nodes up here like this. What we assume with a binary search tree is it's not going to be a straight line. We're not going to have that worst possible scenario, and we treat it as if it is O of log n. We don't treat this like an O of n data structure. So for lookup, insert, and remove, we treat this as if it is O of log n. Now let's compare this to a linked list for lookup, insert, and remove. So if we're going to do lookup with a linked list, say we're going to look for the number 91. We start at the beginning and we iterate through the list until we get to the number 91. And because we have to iterate through, this is O of n. So a binary search tree is better than a linked list in this situation. How about if we're going to remove an item and we're going to remove it by value? Once again, if we use the 91 as our example, we're going to iterate through the list, get to the 91, we're going to remove that. That's O of n because we had to iterate through the list. Also, in this situation, a binary search tree is better. Now let's look at insert. Our linked list here is sorted, but there is zero advantage in a linked list to sorting your data. So if you're going to insert a node, you would just append it to the end. And that is O of 1. So I want to point this out because if you get a question, say in an interview, and they say, we need to be able to add data to a data structure very quickly, but retrieval speed is not very important because we're not going to go retrieve things very often. But we could have bursts of data coming in, and we want to make sure nothing gets dropped. So we want this to be able to be added as quickly as possible. If you were going to choose between a binary search tree and a linked list, which one would you choose? Well, the linked list is better for that situation. There is no data structure that is the best answer in all situations. That's why it is important to understand the big O of all of the operations that you would do with a particular data structure. So let's look at all three of these side by side between linked lists and binary search trees. So insert is faster for a linked list because we can just add an item onto the list and it's O of 1. But lookup is O of log n for a binary search tree, and the same is true for remove. And if you look at lists and you compare them to binary search trees, all of that is the same. Inserting an item, you can just put it on the end, O of 1, but lookup and remove by value will be O of n. Now, if you're looking up by index, obviously that's very fast. But if you're looking up a value or removing a value, you have to iterate through the list. And that is our overview of binary search tree, Big O.